Hi boys and girls, this is lecture 5.5. The topic, the Fundamental Theorem of Calculus. This will be part 1 of this discussion. In the past couple of lectures, we learned that the definite integral can be used to determine area under a curve. Those conclusions lead to the fundamental theorem of calculus. If a function f is continuous on the closed interval ab, and uppercase F is an antiderivative of f on the interval ab, then the integral from a to b of f of x dx is equal to antiderivative f of b minus antiderivative f of a. When applying the fundamental theorem of calculus, the following notation is convenient. Notice we have the integral symbol, we have the lower endpoint of integration, the upper endpoint of integration, the function. Dx represents the variable that we're integrating with respect to, then equals the antiderivative from a to b. Notice we just changed from the integral sign to a bracket to the right side of the antiderivative with the same endpoints of integration. And then we plug b into f of x and plug a into f of x and then subtract the two to get the value of the definite integral. Here's an example. If we're integrating x cubed dx from 1 to 3, the antiderivative is x to the fourth over 4 from 1 to 3. So first we plug 3 into the antiderivative, 3 to the fourth over 4, minus, and then the lower endpoint in for the antiderivative, minus 1 to the fourth over 4 equals 81 over 4 minus 1/4, which is 20. Now that is the analysis of how you find a definite integral, but remember also that means that the area under the curve x cubed from 1 to 3 is 20. Let's practice evaluating a few definite integrals. We have the integral from 1 to 2 of x squared minus 3 dx. The antiderivative then is going to be, if we add 1 to the exponent, x cubed over 3 minus, and the antiderivative of 3 of course is 3x. And then now we are going to plug in the endpoints of integration 1 to 2. So here is the antiderivative. Remember, this is now capital F of x. And to evaluate this definite integral, we first plug 2 into the antiderivative, and then we plug 1 into the antiderivative and subtract those two values. So this is going to be 2 cubed over 3 minus 3 times 2 minus 1 cubed over 3 minus 3 times 1. This will be 8/3 minus 6, and then minus 1/3 plus 3. Well, 8/3 minus 1/3 is 7/3, and negative 6 plus 3 is negative 3. If I change this to 9 over 3, this becomes negative 2/3. And that's the value of your definite integral. Now let's do the second example. I'm going to rewrite this as the integral from 1 to 4, putting the 3 on the outside, and then I'm going to write this as x to the 1/2 dx. Remember, there's a rule which says you can take the constant and put it to the outside of the integral sign, which is what I'm doing here. Now integrating this using the power rule, I'm going to add 1 to the exponent, which gives me 3/2, and then dividing by 3/2 is the same as multiplying by the reciprocal 2/3. So this now becomes 3 times 2/3 x to the 3/2. Which simplifies even further to 2x to the 3/2 from 1 to 4. Now, to evaluate the antiderivative, we plug 4 in for x and then 1 in for x and subtract the 2. So this will be 2, 4 to the 3/2 minus 2 times 1 to the 3/2. When we take the square root of 4, that's 2, cube it, that's 8, times 2 is 16, and then minus 2 times 1, which is 2, gives us a value for this definite integral of 14. For this last example, the antiderivative of secant squared is tan x, and we're going to evaluate that from 0 to pi over 4. First, we put the upper endpoint of integration into the function. That's going to give us tan of pi over 4. And then we plug the lower endpoint of integration in, subtract, of course, the 2, tan of 0. This becomes 1 minus 0, which is 1. Now let's evaluate a definite integral involving absolute value. Since we've learned that the definite integral represents area under a curve, let's see what that means for an absolute value function. We're interested in the area from 0 to 2, so this is the interval that we're looking at. But remember that an absolute value function really contains two curves embedded within one function, and we can see that here at 1/2 the functions split. To the left of 1/2 we have one line, and to the right of 1/2 we have another. In fact, this absolute value function can be written as a piecewise function. We can say that it is the curve negative 2x minus 1 when x is less than 1/2, and it is the curve 2x minus 1 when x is greater than 1/2. So since we'll be looking at area under this curve from 0 to 1/2 and area under this curve from 1/2 to 2, this means we're going to have to split our definite integral into two integrals representing the different curves. So our first integral will be from 0 to 1/2 of negative 2x minus 1. And then we'll add to that the definite integral from 1/2 to 2 of positive 2x minus 1. When I distribute the negative, I'm going to have negative 2x plus 1 for this first integrand from 0 to 1/2. And then, of course, the second one does not change. Now let's find the antiderivative. For this first integral, it's going to be negative x squared plus x, and again, we're evaluating from 0 to 1/2. For the second integral, it's going to be x squared minus x, and we're evaluating from 1/2 to 2. First, let's evaluate this integral. I'm going to have negative 1/2 squared plus 1/2, and then I would be subtracting the value of the integrand when I plug in the lower endpoint of integration, which in this case is just going to be negative 0 squared plus 0. And we're going to add this now to the value of the other integral, which is going to be 2 squared minus 2, and then minus 1/2 squared minus 1/2. Lots of brackets going on here. I'm not really sure how many I have. Let's find some space and change colors just for fun. So over here now I'm going to have negative 1/4 and then plus 1/2. This really doesn't do anything since it's 0. Now here I'm going to have 4 squared, 2 squared, which is 4, minus 2, and then this is going to be minus 1/2 squared, which is minus 1/4, and then minus a negative 1/2, which is plus 1/2. So we end up with 4 minus 2, which is 2, 1/2 plus 1/2, which is another 1, and then negative 1/4 and negative 1/4 is a negative 1/2. So that's 3 minus 1/2, which is 5/2. And that is the total area under this absolute value curve from 0 to 2. Using the fundamental theorem to find area. Find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2, the x-axis, and the vertical lines x equals 0 and x equals 2. Essentially, this is given to you as a problem in which you are to find area. It's not already set up as a definite integral for you. So the extra step here for you is to set up the definite integral. We're finding the area between this curve, the x-axis, and the vertical lines between 0 and 2. So it's the area under the curve in this region. And we know that the way we do that is to take the definite integral of this function from 0 to 2. So let's set that up. Our lower endpoint of integration is the leftmost point on the interval 0, and our upper endpoint of integration is the rightmost endpoint of the interval. We're evaluating the function 2x squared minus 3x plus 2, and we're integrating with respect to x. So let's find the antiderivative. Adding 1 to this exponent is 3, which gives us 2/3 x cubed. Adding 1 to this exponent is 2. That will be minus 3/2 x squared, and then plus 2x. And of course, we're integrating from 0 to 2. So we'll have 2/3 times 2 cubed minus 3/2 times 2 squared plus 2 times 2. And then when we plug in the lower endpoint of integration, since all of our terms have, I should have put just a minus there, all of our terms have x's in them, this becomes minus 0. It's not going to figure in the final calculation. So this will be 2/3 times 8 minus 3/2 times 4 plus 4, which gives me 16/3 minus 6 plus 4. So 16/3 minus 2. And if I change this to a 6/3, 16/3 minus 6/3 becomes 10/3. The value of this definite integral, but also the area under this curve from 0 to 2. You probably recall that there was a mean value theorem for differentiation. There is also a mean value theorem for integrals. The word mean in these contexts is referring to an average, so we're going to develop an average value function for integration. If f is continuous on the closed interval AB, then there exists a number c in that closed interval AB such that the value of the definite integral from a to b of our function will equal the function value at the c that we find times the difference between a and b, the width of our interval. Notice I have a function f of x drawn here, and the pink shaded region underneath represents the exact area under the curve. In this first graph, I have chosen a c value that occurs at the lowest point on the function. Along the function from a to b, this is the lowest point on the curve, and at that c value I've chosen the function value there. If we let that be the height of a rectangle, and the width is the distance from A to B, you can see that the area of that rectangle is definitely less than the actual area under the curve from A to B. In the second graph, I've chosen a c value that gives the highest point on the curve. This function value on the interval from A to B is the highest function value, and if we let that be the height of the rectangle, and again the width is from A to B, you can see that the area of this rectangle is definitely more than the actual area under the curve. Well, the mean value theorem says we can find a c value between a and b such that the function value becomes the height of a rectangle, and of course the width is a to b, and the area of that rectangle will be exactly the area under the curve. So let's go back to this definition. Some c value and the function value there times the width of the interval from a to b forms the area of a rectangle, which is exactly equal to the value of the definite integral from a to b of our function f of x. So what is the average value of a function? The value of f of c, remember we found the c and the function value or the height at that c, given in the mean value theorem for integrals, is called the average value of f on the interval AB. So that function value at the c that we find is the average value of a function. So the definition of average value of a function on an interval. If f is integrable on the closed interval AB, then the average value of f on the interval is 1 over b minus a times the definite integral from a to b of f of x dx. Notice this is simply a rearrangement of the formula we saw previously. Previously, we saw this. The value of the definite integral from a to b is equal to f of c, again that's at some c, a height, a function value, times a width a to b. We recognize this as an area of a rectangle which would equal the value of the definite integral. Since we have determined that this is the average value, to solve for it, we divide both sides by b minus a. So now that results in this formula. 1 over b minus a times the definite integral from a to b of f of x dx is equal to f of c. And this f of c, this function value at some c, is the average value of the function. In this last example, we're going to find the average value of a function. Find the average value of f of x equals 3x squared minus 2x on the interval 1, 4. So here's our interval from 1 to 4. The area under the curve would be this region. But of course, in this example, we're not just finding the area under the curve. We're looking for a function height somewhere between x equals 1 and x equals 4, which is the average value of the function. Here's the formula that we'll be using. 1 over b minus a, basically 1 over the width of the interval, times the definite integral from a to b of our function. So in this particular problem, that's going to be 1 over 4 minus 1 times the definite integral from 1 to 4 of 3x squared minus 2x dx. That's 1/3 times the antiderivative, which is x cubed minus x squared, and that will be evaluated from 1 to 4. This is then going to be 1/3 times 4 cubed minus 4 squared, and then we'll subtract the value at 1 cubed minus 1 squared. Of course, 1 cubed minus 1 squared is 0, so this is not going to give us an actual value. And that means we're going to have, moving over here, 1/3 times 64 minus 16, 1/3 times 48, which is 16. Now let's interpret that result. 48 is the value of the definite integral. It is the area under the curve from 1 to 4. 16 is the average value. The function height 16 is the average value of the function. Here's another way to look at it. If we constructed a rectangle and the height was 16 and the width was the distance from A to B, which is 3, isn't it true that the area of that rectangle, 16 times 3, is 48, which is equivalent to the exact area under the curve on the interval from 1 to 4. So the average value of a function is that function height which forms a rectangle on the given interval whose area is equivalent to the area under the curve on that same interval. That's it for today's lecture. Love is like the first fundamental theorem of calculus. Guarantees an antiderivative for every continuous function, but not that they are always easy to find. Calculus and love, almost the same thing, really. God bless you, boys and girls.